bunch of topics today. So yesterday we looked at various random walk models, freely jointed chains, freely rotating chains, the idea of a persistence length, and finally the cone model, right. So today we will begin by looking at distribution functions. Okay. And we will begin by looking at the distribution function for a freely jointed chain. So, if you recall, the freely jointed chain was a set of monomers connected by rods, where each rod was free to take any arbitrary orientation, right. So, we could and this was L1, L2, L3, the bond vectors going up to L n minus 1, this one. And so, we are interested in the distribution function. I will write it as psi that, okay. So, in general one would write it as for these bond vectors all the way to L n minus 1. I am going to use a shorthand notation and represent it like this, okay. This meaning the set of all L's, right. Now, because their orientation is completely independent of each other, we can decompose this distribution function into a product of n minus 1 distribution function. So, this would be pi, that is the product sign, I going from 1 to n minus 1 of psi Li. So, I mean if I were to expand it, what I mean is this is psi L1 times psi L2 times all the way, right. And so, the question is, what is the distribution function for any individual bond vector, and we write that as 1 by 4 pi L squared times delta L minus L, okay. And what this means is that the delta function is non-zero only when your L is or the magnitude of L, I should say, sorry. We are forcing the magnitude of L to be fixed equal to the bond vector length L. Now, if you did and this distribution function is normalized. So, if I do and if I wrote integral dl psi L, this will be equal to 1. And I am assuming you are all familiar with delta functions. The properties we are interested in, so for if I have a delta function defined this way, you know that the area under the delta function is equal to 1 if you integrate it from minus infinity to infinity, and if you integrated any function then what the delta function does is picks the value of the function at the location where it peaks, right. So, that is the idea here, that if you integrated, if you carried out this integration, convert it to spherical coordinates. So, you will get the magnitude L, theta and phi. The theta and phi integrals give you this 1 over 4 pi factor, and the L squared will take care of the integral over the magnitude, and then delta function will make sure it is equal to 1. So, that is the way you get the normalization, and so this is just saying that the bond vector can be anywhere in a sphere, okay, of radius L, right. So, that is fine. Now, what we are interested in, you recall we were interested in the end to end vector of a freely jointed chain, which I denoted by R e, right, and R e was the last bead location minus the first bead location, or the sum from I1 to n minus 1 of all the bond vectors. So, if you add it up, you would get the end to end vector. So, we are interested in asking what is the probability that the end to end vector has a certain orientation and magnitude given by RE, right. So, there are two ways of deriving this result. One is a formal way and the other is an informal or a hand waving argument, and I will do the hand waving argument first to give you an idea what the solution is. So, if you imagine you have a really long chain, right, and now let us break it up into a bunch of sub chains. So, the really long chain has a certain end to end vector RE, right, but each of these sub chains also have end to end vectors, right. So, we would call this U1, U2, U3 and so on. Now, because the subchain is made of bonds that are independent of each other, each of these end to end vectors of the subchains are also independent of each other. And we know that RE would be the sum of all these subchain end to end vectors, right. Let us say there are m of them. And each of the subchain end to end vectors are identically distributed. They have the same distribution because they are the same freely jointed chains. So, what we are doing is adding up a sum of identically distributed vectors, right. And we know, and this is essentially the situation that the central limit theorem deals with, which says that if I have a bunch of random variables x1, x2, x3 all the way to xm, right, and they are all identically distributed, then their sum is distributed by a Gaussian distribution. Okay. This is a famous result, and it really does not matter what the individual distributions are of the xi, as long as all of them are the same. And the other constraint you require is you need for the central limit theorem is that the variance is bounded. Okay. This does not apply to situations where you have pathological distribution functions. So, then what you get is that the probability that the of x is a Gaussian distribution, right, and this is what a Gaussian distribution would be, where psi is your average x, okay, and sigma squared is your variance. Now, so we borrow the same idea and say, well, we have got these subchain end to end vectors u1, u2, etc. are all independently distributed, and so their sum must be a Gaussian distribution. So, the end to end vector, if you have sufficiently long chains, if m is large enough, is nothing but a Gaussian distribution. So, we would say the probability that the end to end vector has a certain value Re is, and now you have to recognize that this is a 3-dimensional. Okay. So, you get 3 over 2 and this is 2 pi and this would be Re squared. Okay. Because you can think of Re as having Rex, Rey, Rez, the 3 components, in each of them is a Gaussian distribution, and then they add up to be this. Where we know that Re is 0, right. And we know Re squared, which we derived yesterday, was L squared times n minus 1. So, this is an important result that we will need for a lot of our work, okay, that the end to end distribution is a Gaussian distribution. Now, additionally, let us approach this in a formal way, right. How would you find the distribution function for the end to end vector without doing this simple argument? Then what you would do is, this is how you would write it formally. So, this is the property of the end to end vector, and you integrate over all these bond vectors dl1, dl2 and so on dln minus 1 times psi of this set of bond vectors times a delta function okay. So, what does this mean? I mean, obviously, if I only did the integral of the psi, that is normalized, it will be 1. But what this is saying is that you have to contract. So, this is called a contracted distribution function. So, it says of all possible values that L1, L2, n minus 1 can take, only pick those such that the sum of the Li are equal to Re. So, just as you saw, the property of the delta function was to pick the value of the function where the delta function fired, right. And so, essentially you are saying, well, I have got this distribution function that describes all possible values that Li can take, but I only want it to fire when their sum is equal to Re. Okay. So, this is what we would have to evaluate formally. So, I am going to give a result here without proof, and this is essentially the representation of a delta function in Fourier space. Okay. So, I say this is dk e to the power of I k dot x. Okay. This is how one can represent a delta function in Fourier space, and I will show you in a minute why this works. I will not prove how you get this result, but you know that Fourier transform is defined in this way, right. Integral dx e to the of, if f of x is a function, that is how a Fourier transform is defined, and then the inverse Fourier transform would be that is the inverse Fourier transform. So, to show you how it works, let us evaluate this integral over here. Okay. So, 1 over 2 pi cubed integral dk, and for f tilde k I will substitute the expression I have above, right, which is integral dx f of x e power minus I k dot x, and we will call it x prime because it is a dummy variable inside an integral, times e power I k dot x. Now, we can switch the order of integration around and bring the x integral out and take the dk integral in, and so I would call this integral dx prime of, we can bring f of x prime out, right, 1 by 2 pi cubed, and now do the dk one, and if I combine the two exponentials I will get integral I k x minus x prime, right. Have I got everything there? I have just regrouped it and rearranged the integral. Now, you recognize that this is nothing but our definition of a delta function, right. So, this is integral dx prime, and these are vectors f of x prime delta of x minus x prime, right. And then from the property of the delta function, you know this has to, it picks the value of f at x, and so this is nothing but f of x. So, which is what it should be, because that was our definition of what f of x is, right. But you saw that by using this representation of the delta function, you got it back, that it was consistent. So, that is just to convince you that in fact, that this is the delta function, this representation. So, now let us go back to our contracted distribution function and rewrite it. Maybe I will start here.
So, actually what you did looks very similar to what one does for Kramer-Kronig relationship.
This is often, it is a trick that is often used in lots of different contexts. So, it is yeah. Okay. So, let us write this. We want to know P of Re, and we are saying this is an integral, and I am going to use a shorthand notation. dl means the set over all Li, right, times psi, and this was that set, times the delta function Re minus sigma I 1 to n minus 1 Li. Okay, that is what we wanted. Now, I am going to replace this delta function by its Fourier representation. So, I will rewrite this as integral dl psi of Ln, right, and this was 1 over 2 pi cubed integral dk e to the power of I k dot Re minus, so whatever was in there, sigma I 1 to n minus 1 Li. Okay. Now, so let us bring the again I am going to shift the order of the integrals, and so let us do the dk one here first, and I will remove only the Re term, because the Re is not involved with the other integral. So, this is just Ek dot Re minus Ik dot sigma Li, right. So, I can write this as E I k dot R E times 1 over 2 pi cubed integral now dl. Now, this psi, if you remember, was a product of all these individual psi's, because they were independent of each other, right, times e to the power of, we are left with I k dot. So, let us maybe write it L1 plus L2 plus all the way to Ln minus 1, right. Now, e to the power of a sum is the product of the exponentials. So, I can write this as integral dk e to the power of I k dot Re 1 over 2 pi cubed, and now there is a bunch of integrals. So, and I will separate them. So, the first one would be integral dl1 psi L1 times e to the power of I k dot L1, right, times integral dl2 psi L2 e to the power of I k dot L2, and so on, n minus 1 such terms. Then you recognize that each of them is the same, they are all the same integral, okay, and you have n minus 1 copies of them. So, and what is this? It is the integral of E I k dot L multiplied by the distribution function. How does one represent that? It is nothing but the average, right, the a property multiplied by the distribution function integrated over all variables is nothing but the average. So, what do I get here? So, I will get this is equal to 1, oh, let us keep the 2 pi cubed out here, 2 pi cubed integral dk E dot I k dot R E times this average of E power I k dot L. Does not matter, I do not have to keep the index on the L, because it's just a dummy variable, and you're going to integrate it out when you do the average to the power of n minus 1. There are n minus 1 of these, and so this is the end-to-end distribution function. Now, I am not going to go into the algebra of how you evaluate this, it's quite tedious, but this turns out to be nothing but sine k l over k l, okay? And so the whole thing would be raised to n minus 1 terms, and if you worked it out, then you find that indeed it's a Gaussian distribution. So you can see it was advantageous to motivate it simply rather than just do it formally, because if you do it formally you get the same result, but it's much more tedious. Okay. So we've got the distribution function of the end-to-end vector now. Now where am I? Yes, you're right. Sorry. Thank you. Okay. This is the end-to-end vector from bead 1. Yeah, I am consistent in my errors. Okay. So this is the end-to-end probability distribution from the first to the nth bead, right? But if we picked any bead m and another bead n, and we connected them with a vector and asked what is the probability distribution of this end-to-end vector, if m minus n is large enough, right, then you can do exactly the same argument, and that should also be a Gaussian distribution. So you can show that R m minus R n, the probability of that would be 3 over 2 pi R m minus R n the whole squared, right, 3 by 2 e to the power of minus 3 over 2, and same thing here. And here R e squared is R m minus R n the whole square. Okay. So any two beads connected by a vector will also obey a Gaussian distribution, and all these ideas are very important for the following reason. So we've been arguing all along that we want as simple a model as we can work with, and we've seen that the local structure of the chain only comes in through L, and the number of essentially things scale with the number of monomers n. So we can go to the limit of the simplest possible model for a polymer, which is still a random walk model, which is called a Gaussian chain. Okay. And what you assume here is that this distribution function L, which we knew its form for the freely jointed chain, is in fact a Gaussian itself. So you write this as 3 over 2 pi L squared okay. That is that the instead of having these connector vectors or the bond vectors as having a fixed length, it turns out that if you have what is called this Bead Rod model, then it is much harder to compute with it. And really, when you are interested in large scale properties, you could even take not bother and just, because here we have L squared equal to L squared, as long as the local connector vector or the bond vector has a root mean square value equal to L, then you essentially got all the large scale properties that you want. So because these are independent of each other, then the chain as a whole, okay, is also a Gaussian distribution, right. So, you multiply minus one of these. So, if you did that, you would get 3 over 2 pi L squared 3 this is over 2 n minus 1 over 2 e to the power of 3 over 2 L squared, and here I will write this as sum over I 1 to n minus 1 of r I plus 1 minus r I whole squared. Okay, because each of the Li is r I plus 1 minus r I, right, where r I is the location of the monomer. So, if I am going to add up all of them, I mean if I multiply all these exponentials, I add the exponent and that is what you get. So, this is then the distribution function of the chain as a whole, where each connection between individual monomers is also Gaussian, okay, and this is called a Gaussian chain, and it is the simplest model, and it is used a lot in polymer physics to derive all the main results that we know. Okay. So, having established that, let us move to the next thing that I want to cover. And that is what is the free energy of a freely jointed chain. Okay. So, you all know that the entropy, right, is Kb log of the number of possible states a system can occupy, right. Now, we want to ask ourselves that if I introduce omega n comma Re, or let us say nk, we are looking at, let us say we are looking at a Kuhn chain, and say this is all the states that a freely jointed chain with nk Kuhn steps can occupy, such that the end to end vector is Re. Then I call the entropy of that system Kb log Okay. Now, we can ask ourselves what is the probability that a Kuhn chain with nk Kuhn steps has an end to end vector Re. Now, we have just answered this question in a different way, but now in terms of the number of states that the chain can have, it's you can use the frequency definition of a probability, right. It is the total number of states that a Kuhn chain with nk steps has that have an end to end vector Re divided by all possible states, right. That is just the probability by a frequency definition. The number of times this event occurs by the total number of all events, right. And what are all the events? Well, I have a chain with nk Kuhn steps, and Re can take any possible value. That is the complete space you have. Of that, what fraction have got this end to end vector that I am interested in, Re. So, that is the definition of the probability. So, now from here I can say, well, this implies that omega nk comma Re would be probability of nk comma Re times, let us use a simple notation for this integral, I will just call it z, okay, like a partition function, but just for simplicity, because it will simplify the algebra. So, that now S, which is nk comma Re, is Kb log of this omega, right. So, it is log of this probability nk comma Re plus Kb log z, right. Notice that this z does not depend on Re, because you have integrated out the RE dependence. Okay. But we have just found that this probability P has the following form. Now, I am going to substitute the fact that this RE squared we found was NKBK squared, right, yesterday. That was what was here in the denominator, to the power of 3 by 2 e to the power of minus 3 over 2, and then this is RE squared divided by NKBK squared for a Kuhn chain. So, now I have to take the log of this. So, the log of P NK comma RE, again it is the sum of two terms. So, it is 3 over 2 log 3 over 2 pi NK BK squared plus, and the log of the exponential is just the exponent. So, this is just minus 3 over 2 RE squared over NKBK squared, right. So, then I can now write my entropy from above as S NK comma RE was KB times this log. So, I will keep this 3 over 2 KB times RE squared over NKBK squared. Okay, that comes from here, and then I need this term. So, that is plus 3 over 2 KB log 3 over 2 pi NKBK squared, and finally, I had that KB log Z, right, from up there. So, plus KB log Z. Now, notice that these last two terms do not depend on RE, right. So, I could simply say that this is minus 3 over 2 KB RE squared over NKBK squared. This is the main term that depends on RE and NK, and this depends on NK. So, I will just say this is NK comma 0, where this is like could be for RE equal to 0, or it does not matter, right. It is just a constant addition to that entropy term. Now, from equilibrium thermodynamics, you are all familiar that the Helmholtz free energy in this case is given by U of NK comma RE minus Ts, right. U minus Ts is your Helmholtz free energy. So, now because we are dealing with a freely jointed chain, it does not have any internal interactions. The rods are completely free to move. This would be different if there was some potential energy of interaction between the different monomers. Then I could not say U was independent of RE, but it is in this case. There is no internal energy. So, we could just write that as U NK comma 0 minus, there are two terms here. So, this would be 3 over 2 KBT over NKBK squared times RE squared, right, and this term minus this would, oh sorry, this becomes plus because there is a minus and there is a minus here, and then this would be minus. So, this would be minus Ts NK comma 0. Okay. Now, I can combine these two as a kind of Helmholtz free energy, that term that does not depend on RE. So, I write A of NK comma RE to be this first term 3 over 2 kBT over n kBk squared times Re squared plus A of nk comma 0. Okay. So, this now is the free energy of a freely jointed chain. Now, let us imagine we change this free energy by changing the end to end vector by a small amount, right. So, I would say dA, the change in this Helmholtz free energy due to a small change in Re would be the derivative of this with respect to Re, right. So, this would be 3 over 2 kBT n kBk squared times 2 Re time dotted with dRe. If I took the differential small change in the Helmholtz free energy because of a small change in the end to end vector. The other term is a constant, so it does not contribute. Now, what do we know from thermodynamics about the change in the Helmholtz free energy in an isothermal system? It is equal to the work done, right. The work done on a system under isothermal conditions is equal to the change in the Helmholtz free energy. So, the right hand side is the work done by changing the end to end vector by a small amount, right. And what is work? Force times displacement, right. So, this we did this displacement. So, this must be the force, right. So, I now can say that dA is in fact this force dotted with Re, and the force is, and the 2 and 2 cancel. So, 3 kBT over n kBk squared times Re. So, you recognize that the force is linear in the end to end vector when I make a small change in it, right. And this is like saying that it is a spring, like a Hookean spring with this prefactor being the spring constant. So, the resistance is coming completely from entropy to stretching the chain. So, when you try to stretch the chain, you are experiencing a force that is coming because if you stretch the chain, you are reducing the number of possible states it can occupy, and that is this S term that we have calculated, right. And so, when the entropy drops, you are reducing the number of states it can occupy, and then the chain resists it. Okay. So, that is why it is called an entropic force, that you will see that description often for this, which is like a spring. And notice that this entropic the spring constant depends on the temperature T. So, rubbers for instance actually become stiffer if you heat them, because the spring increases, the resistance increases, whereas metals will soften if you heat them, because the source of the elasticity is not entropic. Okay. So, that is an important thing that we need, and this now is the foundation for people using bead spring chain models for polymers, because we can now introduce you to the first polymer kinetic theory model that is very commonly used, the Rouse model, introduced by Rouse, where he said, okay, I have a polymer, I will now subdivide it into, let us say, beads. Each bead is connected to the other with a spring, and the spring is Hookean, and it represents the fact that there is resistance to stretching if I try to stretch any two segments in the chain. Okay. So, that is the foundation of the Rouse model.
So, Ravi,
yeah.
The above expression suggests that when both the ends are at the same point, you have maximum number of configurations, and therefore force is minimum at that point. Means the entropy is maximum when you have both the points are absolutely on the same dot. The end to end distance Re is equal to 0.
Is that the case? If we look at the expression for the entropy, that's not the case, right? Well, it is, I suppose, if you look at it as a negative.
So, but the chain has distribution. So, how we reconcile that?
I am not sure if you force the end-to-end vector to 0, you are constraining the number of states that it has. If you allow it to be free, it would have all the possibilities of any end-to-end vector along with the one where it is 0, right. So, I do not believe that is the low has the maximum entropy. We would have to look at that in some more detail.
When you have a spring, like compressing it or extending it is like equal and opposite, but here like intuitively it's not obvious why.
No.
But the expression says it's the same.
Whether you decrease the end-to-end vector or you increase it. You could decrease and still lose the number of states that you have. It does not matter. As long as, yeah, it could go in either direction.
The expression says it's symmetric, right?
About the 0.
And I mean like compression and extension are both like equal in the force you apply.
Yes. So, we would, if I looked at a single spring in a bead spring chain model, I would say it costs for, so there is a rest state for the spring which we will find as the equilibrium state, and then you stretch above that and that costs. So, in a polymer, if it was in the coiled state, that is its equilibrium state, where the end-to-end vector could be anywhere. But if you grabbed hold of them and tried to stretch your chain into an extended configuration, that is when you pay a penalty. So, I am not sure that one tries to compress it and that would lead to the same thing. Yeah, I think it is similar to what Yogesh was asking me, but I have not thought along those lines. I need to think about it. So, I am introducing the Rouse model now. And so, we will number the beads 1, 2, 3, I, n minus 1, sorry, yeah, n minus 1 and n, and we have an origin in space O, and here this is the bead position vector R1. We will have a center of mass, and we need this, I will denote it by RC, the center of mass, and so an arbitrary bead, and I am now going to use the notation in Bird, Stewart and Lightfoot, because that is the where I have got all this stuff from, and they denote beads with a Greek index nu. So, that would be the position vector of bead nu would be R nu, and from the center of mass its location is denoted by this R nu. Okay. So, we have the definition of RC is 1 over n sigma I going from 1 to n of R nu, that is where the center of mass is located. Okay. And the bead positions are R nu. So, the velocity of a bead dr nu by dt we denote by R nu dot. Okay. So, that is your bead spring chain model introduced by Rouse, where each is a spring. And now, what we are interested is in what is the equilibrium distribution function of this bead spring chain. Okay. And in general, right, it has a velocity r dot nu. So, each bead has a momentum m r dot nu, right, and one could write the kinetic energy of your chain as half sum nu going from 1 to n of m r dot nu squared, right. This is the total kinetic energy of the chain, and this in terms of the momentum would be written as 1 over 2 m nu 1 to n of p nu. Okay. Now, what about the potential energy? I am going to assume I have to introduce these connector vectors, which we have not done. There are connector vectors connecting each of these beads, which are denoted by q. So, this is q1, q2 and so on. So, qi would be r I plus 1 minus r I, similar to the LIs that we were seeing before, but these are called qi, and but they correspond to the spring connector vectors, okay, between the beads. So, you could either describe the configuration of the chain in terms of R1, R2 all the way to Rn, or equivalently you could say what is the center of mass and what are all the connector vectors, but there are n minus 1 of them. The total would still be n variables, 3n actually, because each is a vector, variables to describe the configuration of the chain. Now, in terms of the potential energy, we are going to assume that it is only a function of the internal coordinates. Oh, sorry, yes, thank you. It is extremely annoying when you are seeing a lecturer doing something wrong and you can't tell him, right. When I look back sometimes in my notes and say, oh my God, so stop me and correct me, I would be grateful for that. Okay. So, we are saying it does not depend on the absolute position of the chain in space, and in general we will only be interested in those situations, because in fact kinetic theory has been largely developed for these homogeneous flows and the absolute position does not matter. So, that would be your potential energy. So, then your Hamiltonian then, as you all know, is the sum of the kinetic energy and the potential energy. Okay. And let us now that we know the Hamiltonian, at equilibrium, you know, from canonical from a canonical ensemble you can find probabilities. So, first let us define what is this probability distribution we are interested in. So, I will call F equilibrium, which is a function of the momenta of all the beads and the all the bead connector vectors to n minus 1 as the probability distribution of finding a bead spring chain with momenta p1, p2, p3 etc., and bead connector vectors q1, q2 so on, right. And this now from equilibrium statistical mechanics is given by e to the power of h over k b t times integral dp, and I am going to use this shorthand for p to denote all the p coordinates and q to denote all the q coordinates, e to the power of minus h over k b t. This is just the partition function, the denominator. Okay. This comes from statistical mechanics, and I know the kinetic energy and I know the potential energy, and therefore, in principle I can find it. Now, for us we are not so interested in the momenta, and I will describe why later on, but we can define the equilibrium distribution function that only depends on q1, q2 all the way to qn minus 1 as integrating out all the momenta dependence from this, right. If you integrate out all the dependence on the momenta, you are left with only the dependence on the bead connector vectors, and I call that the equilibrium distribution function. Now, obviously you can see that F equilibrium dp dq is equal to 1, right, just from the definition, and it has to satisfy that. And similarly, you can see from here that integral psi equilibrium q1, q2 and so on is also equal to 1, because if you integrated this right hand side by dq, you come back to this, which is normalized. Okay, so both these distribution functions are normalized. It is convenient for us to introduce this momentum space distribution function, okay, which is defined. I think I was going to do all of this today. I am just checking. Yes, in this form. Okay, and we will make use of this later when I define some averages. Okay, but let us now assume that these springs are Hookean. Okay, what is the potential energy phi of a single Hookean spring? If my spring constant I denote by h, then it is half hq squared, right? That is the potential energy of a spring. So, for a chain of Hookean springs, then the total potential energy would be some, okay, half k going from 1 to n minus 1, right? That would be the total potential energy. So, if I look at my distribution function, right. So, firstly, suppose I look at psi equilibrium, right, and I said you get it by integrating out the momenta, right. So, dp1, dp2 and so on f equilibrium. Let us do this with the expression that I had, okay, which would be so this was the denominator of f equilibrium, right, and now the numerator I am saying just do this part, right, just integrate out the momentum from the numerator, that should give me the equilibrium distribution function. But I know the Hamiltonian, okay, is a so I could separable into the kinetic energy part, and that is the only thing that depends on the momentum times the part that depends on only the potential energy, okay, because the Hamiltonian was the sum of the kinetic and the potential energies. I can separate it like this, and in the denominator as well I can separate this in the same form. There is no q integral here, sorry, otherwise you lose your but there is a q integral in the denominator, okay. And then you notice that this is just repeated in the numerator and the denominator. So, psi equilibrium formally from statistical mechanics is integral dq e to the power of minus phi over kbt, and the numerator is e power minus phi over kbt. So, that is the formal expression for the equilibrium distribution function of a bead spring chain. But as I just said, the potential energy for Hookean springs, okay, is nothing but half sum over h qk squared. So, I can substitute it in there and I will get that psi equilibrium, and let us use this shorthand, is e to the power of minus half of h divided by integral, and this will be dq1 Is that clear? But if you look at the denominator, you can actually explicitly carry out the integral. Okay, it's what's called a Gaussian integral. So if I have this an expression like this, then it turns out that you can do this integral analytically, and it has this form, pi over alpha to the power of 3 over 2. So let us compare this integral, because I've got exponential of a sum of terms. I can break that into a product of exponentials, and each exponential can be grouped under one of these dq's. Okay, so I can carry out the integral of each of them. So in place of alpha, I've got to have a kbt. That's the Boltzmann. So how long have I been missing it? Only here? Oh yeah, sorry. Okay, so what is my alpha? If I compare with any of these, it's h over 2 kbt, right? So pi over alpha to the power of 3 by 2 would be, I am dividing by h, so 2 pi kbt divided by h to the power of 3 by 2. Each integral contributes these, and there are n minus 1 of these integrals. So we can work out the denominator. So psi equilibrium would be, and that is in the denominator. So this goes to the numerator. I would get h over 2 pi kbt, and there are n minus 1 of these, and then I have the exponential that just comes from here. Okay, I will write it and then we will scroll down. Okay, that is the distribution function, equilibrium distribution function of a bead spring chain. Now, do you recognize that it looks a lot like the distribution function for the Gaussian chain that we had derived already? Okay. What was that? So if you recall, I had written that as psi of ln, right, was 3 over 2 pi L squared to the power of 3 n minus 1 over 2 e to the power of minus half, and this was L squared, and I had sigma I going from 1 to n minus 1 of r I plus 1 minus r I the whole squared. Okay. This r I plus 1 minus r I is exactly the qk's, right? They are the bead connector vectors. So we could compare the two and see that in fact L squared, and I hope this comes out right, is 3 kbt over h. 3 over L squared. Okay, yeah, I think that's right, right? Yeah. and or equivalently the spring constant is 3 kBt over L squared. So, the distribution function, yeah.
We are using h for spring constant, but they defined as Hamiltonian.
Oh, the Hamiltonian H is a funny calligraphic H, right? If I haven't, sorry, I do not mean to confuse you with the notation, but I hope my H looked different. Yeah, there. That H is not the spring to the best of. Oh. Okay, so the idea here is that the Rouse model bead spring chain has an equilibrium distribution function that is exactly the same as your Gaussian chain, okay, at equilibrium. But what we are interested in fact, is in going away from equilibrium and looking at flows, right. At which point in time we will continue to use the bead spring chain model. The Gaussian chain that physicists used is strictly only used at equilibrium to find polymer static properties and dynamic properties. But the bead spring chain, the idea is that you actually lump the mass of the polymer into these n beads, and so this now can be put into flow and the beads feel the drag due to the flow and will exhibit a frictional force and so on. Okay. So, as far as equilibrium is concerned, the Rouse bead spring model is exactly the same as your Gaussian chain, and so you can carry over all the results from there. Now, I want to, how are we doing for time? 10 more minutes, yeah, okay. So, I want to introduce 950, is it that?
We began at 9:15.
9:15. So,
1.5 hours.
11:45,
Yeah.
10:45. So 20 minutes. Yeah, I will. I have some stuff. I'll cover that, and then we can stop for questions. If you, okay. Now that we have established these distribution functions, I want to calculate some average values. Because any experimental probe that you make of a polymer solution is going to measure over significantly long length scales and time scales compared to the size of a polymer. So, it will involve many polymer chains, and so any property you measure is really an average property involving several molecules, and so we need to talk about average properties. Okay. So, how do we define these? So, the for any quantity B, okay, that could in general depend on momentum and so on and your connector vectors, right. We define B, and this is an equilibrium average, as integral of B times F equilibrium of P1, P2 and so on, dP1, dP2, dQ. Okay. That is the general definition of an average. Now, if B depends only on Q and not on momenta, right, then you could integrate out all the momentum dependence here from F equilibrium and be left only with, so then B equilibrium would be integral B of psi equilibrium dQ1, dQ2 and so on, because the, okay, I actually need a couple of steps to show you this, and I have kind of rushed through. Remember, I defined the momentum space distribution function, right, as F equilibrium over psi equilibrium. So, this clearly is normalized, okay, from because if I integrate out the momentum from the numerator, I get left with the denominator, because that is how we define psi equilibrium, right. So, I could write F equilibrium as psi equilibrium times psi equilibrium, and then if I have a quantity, okay, so let us first define a momentum space average as integral okay, that is when you only integrate out the momenta. And if I come back to this expression here and I replace this by the product of psi equilibrium times psi equilibrium, because that is just how it is defined, then I could also write I could write my B equilibrium average in this way. So, in other words, you first integrate B with regard to the momentum variables and then define this average B equilibrium and then integrate out the dependence on Q, right. And in the case where if you look here and if B is only a function of Q, then it comes out of this integral because it does not depend on it, and the remaining integral is just normalized because it is an integral over psi equilibrium, and you just get in that case, right, which is a function of Q. So, doing the momentum average does nothing when the quantity itself does not depend on momenta. And now, of course, if you see here from here, if this is the case, oh, and this needs to be multiplied by psi, sorry, you would get okay, these are just formal definitions of averages that we will need. Okay, now let us calculate, now that we have defined these. So, I have got a bead spring chain, right. And I can define an end-to-end vector here R exactly as before, and R would be sum over from I to n minus 1 of the Qi's, right, because that it is just a sum over all the bead connector vectors. So, now let me find R squared, the end-to-end vector for a bead spring chain. Okay. Now, this could be written as R dot R by the definition of R squared, and this is sum over I 1 to n minus 1 of Qi dotted with sum over j from 1 to n minus 1 of Qj, okay, just by definition. And then I can group these together as sum I j of Qi dotted with Qj. Now, I and j cycle over all 1 to n minus 1, but we can think of first picking out all those where I is equal to j. So, I will write this as a sum of two terms, I going from 1 to n minus 1 where I is equal to j, and then this would just be q I squared plus all the remaining ones where I is not equal to j, where I would have q I dot q j, right. But we know that the q i's are uncorrelated from the q j, each is distributed independently, right. So, I could write the this now as sum over I 1 to n minus 1 of q I squared. These are all equilibrium averages, I am not adding the equilibrium suffix, plus I not equal to j of q I dot q j, and each of these the average value is 0, because they can be oriented arbitrarily. Okay. So, we are left with r squared is sigma I to 1 to n minus 1 of q I squared. So, the question is how do we find q I squared average. Okay. So, we want to find q I squared average, and if we use the definition of our equilibrium distribution function, this has to be q I squared, and let us keep the sum I squared psi equilibrium. But we saw that psi equilibrium for a bead spring chain is a Gaussian distribution, right. So, what was it now? I will have to cheat and copy from there, I can't remember this. It is this term with the h over kbt's. This one, sorry, the one above this, right. Let's the upgraded version of maybe this PDF annotator has meant okay. No, there is a way of just copying an entire bit. Okay, I should be able to remember this.
So maybe you can simply cut and paste it later.
Yeah. No, we needed to do the algebra. So just tell me if I am wrong. Okay, 3 over 2 pi. So the kbt and this h. I don't think there is a h. 3. 3 n minus 1 over 2 integral dq, and this is sigma I q I squared and e power minus 3 over 2 kbt no, h. Is that right? Did I get the whole thing? Okay. So, now what we are going to do, this is an exponential of a sum. So, you can separate them. So, let us write this here. Okay, I am going to write this as a series of so dq1, dq2, so on, and this is q1 squared plus q2 squared plus so on, and this is e power minus h over 2 kbt q1 squared times e power minus h over 2 kbt q2 squared times so on, right. So, we can so all these products multiply each of these terms q1 squared plus q2 squared. So, let us consider just one of them. So, we will call this alpha, right, for simplicity. So, then let us take dq1, okay, times q1 squared times e to the power of minus h over 2 k bt q1 squared, right, and then you have to multiply it by all the others dq2 e power minus h over 2 k bt q2 squared integral dq3 and so on, and this is only one of the terms plus, right. So, I will put this alpha out, integral, and now you will get dq2 q2 squared e power minus h over 2 k bt q2 and all the other ones dq1 e power minus h over 2 k bt q1 squared and all those, right. Now, each of these integrals, if you take the proper factor from alpha out, because there are n minus 1 of those prefactors, is a normalized distribution function. So, they will all go to 1. So, you are only left with this one to do, right, and you will see each of these is the same in front, and we have n minus 1 of those. So, and they are all dummy variables. So, in the end what you will get is simply n minus 1 q squared, okay. And that q squared was the same as L squared, which was 3 k b t over h, right. So, you get 3 k b t over h times n minus 1, that is r squared. Now, and this is nothing but L squared n minus 1, which we got for a freely jointed chain and for a Kuhn chain and so on. So, you see the properties are being maintained all the time. So, the bead spring, the Gaussian chain had this property, and finally, the Rouse model also has the same end to end vector. Okay. So, I think we have kind of set the foundation now to go on to start looking at flows from this afternoon. Okay, thank you. And if you have questions, yeah, thanks. Yeah.